Yeah, it's a great workshop, and my pleasure kind of to discuss not only what we have done, what kind of content is what has been discussed today. And I think that what I'm going to tell will be somehow relevant already to what people presented, so which makes my life a little bit easier. So at the end of the day, it's a question, at least kind of what we're interested in, how we can digitize self-assembly. And so I will explain what I mean by digitizing. I mean, obviously, it is shown here. It is shown here. It's a question of how we can build kind of structures arbitrarily and by design. So first of all, I want just to stress kind of historical perspective that I think that's a great success in the fabrication, which we have seen, from computer control machining to nanofabrication to 3D printing. It's really due to this point that we can digitize those processes. Now, within last couple of decades, when we have different types of nanoscale components, either inorganic particles or de novo proteins, we don't really have really good ways to integrate in the material systems where you have multiple types of components in kind of pre-designed manner. And this is kind of the question which I personally feel like very timely, kind of in terms of nanoscale manufacturing. So in a way, how our goals, I mean, like what my lab is doing, is trying to ask this question, how we can integrate multiple components really on the level of platform. So it's not like every time we have to develop, something new, but at least to have some commonality, how we can integrate systems which contain both organic and inorganic components, how we can potentially push it to be scalable, robust, and kind of with high fidelity. And I'm not going to discuss much, but also questions related to a reconfigurable system which can utilize energy for specific transformation and affecting functions. But again, it's not going to be discussed much. So the overall idea is based on DNA platform. Obviously, much has already have been discussed, which makes my life easier. So I'm not going to talk about DNA origamis. Everybody already knows about this. So the point on the next level, how we integrate DNA origami with different types of nanoscale object, how this becomes kind of building block from which we're constructing systems. So essentially, the idea is that we can use different, and what I wanted to stress particularly, what I think it's kind of important technologically, there is no ways to create design three-dimensional nanoscale structure materials. All current methods are really kind of typically planar, and I'm not talking about 3D printing because it's not able to get to the scale and integration of the components which is needed. So really the point about 3D, which I wanted to stress. So one point here is how we can utilize, for example, different DNA constructs in the form of, for example, DNA frames to be this kind of universal block. So this is an example of the work which we published, where essentially you can utilize different polyhedra and like octahedra, cube, tetrahedra as a kind of a host for materials. So they essentially can carry different nanocargo. It can be nanoparticles, proteins, and so on. So this allows to decouple the self-assembly processes from the material properties of nanoparticles or proteins, because now they are self-assembly which completely dictated by the kind of valency of the frames. And so we demonstrated you can build different types of lattices based on this kind of directional bond. So we implemented this for different optically active particles like plasmonic light emitting, as well for enzymes, for proteins, like, for example, ferritin, and we demonstrated that you can even release iron while maintaining the fidelity of the structure and activity of the protein. However, if we're thinking about this kind of a platform for building really much more complexly organized materials, first of all, I want to stress kind of aspect about kind of three-dimensional printing at the nanoscale, which is shown here on the top. So we can, for example, utilize three-dimensional scaffold like octahedra, place particle inside. We're talking about scaffold in order of 30 nanometers, this particle being 10 to 20 nanometers. And we can use something which we call molecular stamping. We can essentially transfer on a particle pattern in particular places. And this is kind of this pattern with transferring single DNA. And so we can kind of pattern nanoparticle. As after that, we can release a particle. This particle can be used for making clusters or whatever you would like to do. But essentially, it allows to pattern this kind of individual nanoparticles with approximately 50–60% yield. So, but again, going back to the question how we're building materials. So first of all, this kind of nanocargo can contain different types of objects with different properties as shown kind of in a B. But then it becomes clear that you can embed different material properties and how you can control organization. Obviously, the ideas of coloring bonds using DNA sequences is clear. However, how to implement it really in 3D to be efficient and practically meaningful. So we developed this approach, which is essentially what we call kind of building hierarchical three-dimensional organizations through inverse design of encoded bonds. So what I mean is the following. Suppose you want to define some particular structure which is shown here, and what I'm stressing by hierarchical, that it has multiple length scale embedded in the structure. And this you will see in a minute, kind of some examples. So it can contain particles of different kinds on a different length scale which need to be coordinated with each other, and this motif can be repetitive. So essentially there are three major descriptors for the system. So one of them, how I encode bonds for placing cargo, another how I encode the bonds which coordinate particles in some motif, and how I coordinate different motifs assembled together. What is important, one can imagine you can have with DNA, you can have so many different possibilities. But again, what is really, really important to realize, many of those systems will be kinetically trapped. So for that reason, we're very much interested in what we call information constraint assemblies. It means that we want to minimize number of information embedded in the sequences, and this way you will have redundancy of the components and so on, as well as a much easier pathway. So just kind of realization of this. This is an example of experimental realization where you have a motif here which has a spiral organization of nanoparticles. It's required, if you don't do anything, it's essentially required to have 16 components or unique components with 48 bonds. And through this kind of information minimization, the amount of information is reduced by number 4. So again, it allows us to build the structure. We can verify using small angle scattering as well as different tomography approaches. What I wanted really to stress here, what is important, it's a question of any structure which you can imagine will always have some certain kind of symmetry motif embedded. And so we can take advantage of any structure and to minimize the level of information compression might be different, but it's kind of, in principle, it will be always possible. Now, what is important, obviously, it's important not only to design and build, but it's important to characterize. We have been kind of investing a lot of efforts in essentially different type of characterization. What I wanted to stress here, so regarding the first approach, which I was presenting, we are now developing kind of full algorithm how to do it for arbitrary structure. But I wanted to stress again in a kind of view of this workshop in terms of software tools, there are significant need for visualization and analysis of, by characterizing different methods, because it's not enough, to design something. It's required to check. Particularly, it becomes challenging in 3D. So some of the examples which I just going to show here, we're utilizing all these techniques from TEM to SACS to tomography and so on. And some of the optimization can be done. What you see on the right top corner, it's essentially single crystal, which now can be almost macroscopic. It's 150 micron, which is built from DNA origami, and this is three-dimensional. So it contains kind of billions of origami components. So this is an example of really three-dimensional visualization where we can now visualize on a single nanoparticle level, and we can visualize not only nanoparticles, but we also can visualize this DNA framework. Well, I don't have much time to discuss it, but we have been developing different methods how to convert DNA origami into different inorganic materials. In this case, it's a multi-material which contains iron as a first, then silicon, then gold. And what you see here in this movie, it's not a simulation. This is experimental data, which we're obtaining both for individual particles as well as a kind of framework. So this essentially gives you, kind of all this possibility to consider how we can utilize this kind of DNA-based platform for building real materials, which can be resilient at different temperatures, which contain different properties. So we kind of working on all this type of materials, from superconductive to mechanically robust to magnetic and semiconductor. And again, utilizing what we can embed with nanoparticles, but also how we can convert DNA through different processes into inorganic materials. So the last thing which I really wanted to stress, the way how I see this process of digitizing self-assembly, we need all these tools for design. This is kind of obviously clear. At the same time, we need tools to digitize the process. What you see here in the right corner, this is a liquid robotic platform which can essentially functionalize nanoparticles, build DNA origami, assemble DNA origami, and even silicate some of those structures. And so what is important, it's not just for building. We embedded and we kind of continue establishing how we can do online characterization to essentially to close the loop. Because at the end of the day, it's not only about equilibrium structure, which you can design, but it's also controlling the pathway. And I believe that that's kind of really require a lot of machine learning and AI application in order to streamline the process.
Nice work, Oleg. Could you comment more on, in terms of the functionality of the lattices of the particles? So the original lattices, the particles, they're pretty far apart. So probably there's not going to be much interaction between the particles. But then did you say there's a second step where you can then grow the particles in order to actually have communication between the particles?
So by communication, you mean, let's say, plasmonic?
Yeah, plasmonic, or any other functional communication between the particles?
Yeah. So in principle, the particles that we're using can typically 10 to 20 nanometers. The center distances between those voxels would be probably on the order of 50 nanometers. So if you're really talking about very close plasmonic interactions, probably none. We have some methods which we can regrow particles, and many people know how to do it, but we also can convert the whole framework into inorganic material. So, yeah.
Okay, thank you.
Yeah.
The last one.
Thanks, Dr. Gan. It's a nice talk. So I'm very curious about the mechanical stability of your material. It seems that it's more like a super lattice. So I wonder whether there's some interesting phenomenon.
So we didn't explore the mechanical stability where it's kind of in a DNA form. I mean, we're doing this type of experiment, but we did explore, and we didn't publish yet, the mechanical properties of DNA type of structure when you kind of three-dimensional framework when you convert it into silica. What we see, it's better than any other ceramic material so far. It's very close to the theoretical limit of what is possible for silica.
I think we should go to the break. Yeah. Wonderful. Yes. All right. Thanks.